Okay, so the biggest news right now is a week from today is exam 2. And the topics for that will be everything up through free body diagrams. So I'll finish talking about what I need to for you to do all the free body diagram problems today. So you'll have a week to, get used to that stuff. Remember that all of my exams and quizzes are cumulative, so you need to be ready for old stuff too. The way to get ready for all of the exams is just to be familiar with the thought process in the daily assigned problems. So the more you can redo those daily assigned problems, the better off you'll be. And we have a quiz today, don't we? I didn't bring it. I'll go get it. We need to do this quiz. No, let's do it. No, everybody loves quizzes.
It's like extra 5 points to everyone.
No, it'll be fun. I put some fun surprises in there. No, I didn't really. Okay, it's sitting in my office. I know where it is. But yeah, the more you do these daily problems, the better. I think the people who do well in this class pretty much always tend to do these problems more than once. I've said this before. I think the best way to get ready for an exam is to go through all the problems one by one and just ask yourself, do I know how to do this? Just think about what you do to start this problem. What do you do? And if you feel pretty good about like right away, you're like, do this, then you probably don't have to spend a lot of time on that one at that point, But go on to the next one, and eventually you'll hit some problems where you don't really remember the approach, and then spend more time on those. That's my best advice for getting ready for exams. Okay, any questions about the exam? Yes.
How many questions will be on that?
It depends on what kind of questions they are, but when I write a test, I'm always thinking we have 80 minutes in the class, and I'm always thinking of trying to make a 1-hour exam. So I'm trying to give you a little leeway so you have time to think about stuff. You're not feeling like you're racing against the clock. That's sort of how I approach it. But I'd say it's probably always going to be between 4 and 6 questions. And there'll always be a question on new stuff, and then, what old stuff goes into it. Think of that as just kind of like random. I'm just randomly drawing topics from previous stuff, Okay. Any homework questions? Do you want me to go over any of the homework questions? Yes?
Could you do 3 on weekly assignments?
Okay, I can't do weekly assignment problems because that's part of the evaluation, but I will, let me look at it and see what I feel comfortable saying about that. By the way, I'm behind getting the first weekly assignment grade, and I'm going to get to that this week. So sorry about that. Okay, number 3. This is just, I think if you go back to the vector daily assignment problems, just refresh your memory on that. It's really no different than those problems, I would say. So what you're always trying to do is you're always trying to figure out the counterclockwise angle to go from the x-axis of the coordinate system to the vector, you know? And the vector, so you can just think of taking this vector's tail and putting it one at a time at the origin of those coordinate systems, and then just figure out the counterclockwise angle to get from the x-axis to the vector. And then you'll use cosine and sine and multiply that by the length of the vector. Okay? Yeah. Any other questions? Yes. Yeah. Oh, here we go. Number 2. Okay. So there's the scale, there's the floor. What's the force vector the scale applies to the floor? Okay, so what I'm going to do, so when you draw a free body diagram, you always, anything that you can wrap a complete, anything you could shrink wrap, including parts of objects or combinations of objects, that can be your free body. So I'm gonna choose my free body to be this for the first part. Okay, so the scale is in there and the man is in there. So my free body diagram is like this. So now we're going to go through the steps of a free body diagram. There's a weight force that's equal to the mass times 9.81. This has a 60 kilogram person and a 1 kilogram scale in it. So this is going to be 61 times 9.81. And then we have a pushing force from the ground onto the scale. I'm going to just call that N. Okay? So now if I go to Newton's second law, we have the downward force of gravity. So that is in the negative y direction, and that's negative 598.41. Then we have the upward force N. We don't know what that is yet. And these are equal to the mass of this chosen object, this combination of objects, 61 kilograms, times the acceleration. He's just standing there, so the acceleration is 0. And so we get two equations from this. The x equation says 0 plus 0 is equal to, 61 times 0. So that doesn't help us solve for anything. The y equation says negative 598.41 plus n is equal to 61 times 0. And so you can solve for n, and it says n is equal to 598.41. Okay. So what we've figured out is that the force on the scale by the ground is 598.41 up. Okay, are you with me on that? Because you can plug, excuse me, you can plug this n value back into this vector and you get a vector that says 0, 598.41. Okay, well, if the force on the scale by the ground is 598.41 up, then the force on the ground by the scale is just the same magnitude in the opposite direction. Okay, so anytime you have two things pushing on each other and you're just switching the order that you're looking for, all you do is change the direction of that force. And that's true whether things are moving or not moving, or it's a short, intense impact or a slow, gentle contact. None of that stuff matters. All that matters is at any instant, if you switch the order of two things in contact, then you just switch the direction. What's the force vector the scale applies to the person now? Well, now I'm going to choose a different thing to isolate. So this time I'm just going to isolate the person. So this time there's no scale in the weight. There's only 60 kilograms times 9.81. And then there's a pushing force here. I'll call that something else. I'll call it n sub 2, just to make it clear to myself that that's not the same n we had before. And remember that when you have the n with the serifs on it, that's talking about a normal force. That's not talking about newtons. So that's about to get very important to make that distinction when we start talking about friction. And so that's a free body diagram. So now we can go to Newton's second law. The weight force down is 588.6. No, is that right? 60 times 9.81. Yeah, that's right. The force up is 0n2. The different subscript just makes that a different variable than we had before. And these are equal to the mass of the chosen object times the acceleration, which is 0, 0. The first equation again says 0 plus 0 is equal to 0, 60 times 0. The second one, so it doesn't help. The second one says negative 588.6 plus n2 is equal to 0. So n2 is equal to positive 588.6 newtons. And so the force on the man by the scale is, we already knew that the force vector on the man by the scale was this circled vector. We just didn't know what N2 was yet. Now we can plug N2 in there and we get 0, 588.6. Or another way to write that is, you can see that's in the positive y direction. So you can think of this as an upward force of 588.6. I didn't ask for the force on the scale by the man, but if we wanted that, that would just be the same magnitude in the opposite direction. Or you can also think of it as multiplying the vector by -1. So this would be 0, negative 588.6. Or a downward force with a magnitude of 588.6. Okay? Any questions about that? Are there any other homework? Yeah.
Just like a general question, but
Yeah.
will Monday be Scott grading the material or on the test?
I'd be happy to answer any questions anybody brings related to the test, but once those are done, we'll get on to new material. Any other homework questions?
Could you do
Mhm.
3 as well?
Sure. Okay, so I'm going to start with a free body diagram of the block. We're told that there's a 250 Newton force this way. We know that there's a weight force of the mass times 9.81, so that's 981 newtons. And then there's a pushing force from the ground, so that's perpendicular to the surface toward the chosen body. And I'll call that N. Now we'll go to Newton's second law. And one thing we're going to have to use here is we are going to have to recognize that this is a pretty common thing with these problems. Which way is this free to move? And you don't even have to know left versus right versus up versus down. You just have to think, is this thing going to move along the x-axis or the y-axis? This is going to move along the x-axis. And from this picture, it's pretty clear that the acceleration is going to be in the positive x direction. But you don't even have to know that. We're just always going to assume that it's going to accelerate in the positive x. And if it ends up being negative, it'll give you that on its own. The only thing you have to make a distinction between is x versus y. Okay, so the acceleration vector, we're going to put that in as a0. And we just don't know what that a is. That's what we're going to solve for. So from the free body diagram, we know we have a 250 Newton force in the positive x direction, a 981 in the negative y direction, N in the positive y direction, And then that's equal to 100 times our acceleration vector, which we have already decided is in this form. Okay? So now the x equation here says 250 plus 0 is equal to 100a. And so we can divide both sides by 100, and we get that a is equal to 2.5. Okay? Well, all we needed to figure out was what a is in order to fill out this vector. And so now we'll plug a into the acceleration vector, and we get that the acceleration vector is equal to 2.50. Or another fine way to write it would be, it's pointing in this direction, the positive x direction, and it has a magnitude of 2.5 meters per second squared. Okay? All right. So we talked about the direction of pushing forces. There are two other force types we need to, so let's go back to the list of the force types that we're dealing with. So the first one is the weight. That's the force applied to the object by gravity. And then the second type is contact forces. And there are three of those that we're going to see. The first one is pushing forces. The second one is pulling. And when we deal with pulling forces, we're always going to, they're either going to be applied by cables or we're going to be imagining them being applied by cables. So I'm in parentheses, I'm going to say cables. And then the third one is friction. And so we've talked about the weight. We're done with that. We're done now talking about pushing forces. So we're going to move on to pulling contact. And we're always going to be imagining this as a cable force. Okay, so in a way, I think the easiest way to imagine whether something's being pushed or pulled is to think, could the contact between the two objects be replaced with a string or a rope or a cable or whatever without changing the way it works, you know? So like, if I'm doing this, you know, pulling the calculator along the table like that, you could imagine I could do the same thing by having a little tiny piece of cable here and pulling on the cable to make it go this way. But now imagine if I'm pushing on the board and I replace that contact with a string, that string would just collapse. It wouldn't be the same, okay? So you can think of that as a way to make sense out of pushing versus pulling. So this is when the contact could be replaced by a cable or a string without changing the behavior. The other way to think of it is, I said to think of pushing as if the contacting object is trying to make the chosen object trying to keep the chosen object from invading its space. Remember I said something like that. So like if I push on the board, the force that the board is applying is keeping me from sinking into its space. You know, that's a pushing contact. A pulling contact is like keeping the chosen object from escaping. Okay, so like if I'm pulling on this this way, that force is keeping me, like if that force disappeared, my hand would go this way. Okay, so that's another distinction you can make between these two. So a pulling force keeps the chosen object from escaping. Maybe not successfully. I mean, you can pull something and still go in that direction, but the tendency of it is an attempt to keep the chosen object from escaping. Okay, so like an example of a pulling force. If you have these two objects in contact with each other, well, they're in contact through a cable in this case, and you apply a force to this one, okay? This cable is pulling on each one of these bodies. So you have a pull here, a pull here. And you have a push here and a push here. Okay, well, the main thing we're trying to figure out for all these individual force types is the direction of the force. So the direction of a pulling force, I said that for a pulling force, you could always replace the contact with a cable. So we're just always going to imagine that there's this tiny little piece of string or cable that replaces the contact in any pulling force, okay? And then you have to think about what way the string or cable would face if it was replacing that contact. So the direction of the pulling force is always going to be parallel to that cable. And this time away from the chosen body. So remember, with a pushing force, the force was always toward the chosen body. With a pulling force, it's always away from the body. Okay, and think about the puffy coat thing again. If someone pulls on your puffy coat, it makes it go away from you. That's the direction of the force. Okay, so let's see. Yeah, let me do a little example. So I'm going to do basically this example above. I'll give masses to the two carts. So let's say this one is 15 kilograms and it's connected to one that's 30 kilograms. And then we have a 300 Newton force pulling on the one on the right. And I want to draw free body diagrams for each of these. Okay, so I'll start with the 15 kilogram. So there's the closed outline. And then we have a weight force down that's equal to 15 times 9.81. So that's 147.15 newtons. Now we're looking around the boundary for contact with the surroundings. There's contact at the wheels. That's a pushing force. So the rules for a pushing force say perpendicular to the surface, toward the chosen body. And I'm going to give that the name N15. Just so I can use a different subscript to mean a different variable when I go to the next one. And now if I keep going around the boundary, the next thing I run into, the next place where the surroundings contact the surface, the boundary, is at the cable. That's a pulling force. Cable forces are always pulling forces. So this is away from the body, parallel to the cable. And I'm going to label that one T. That's a pretty common variable. I mean, it's just a variable, but that's a pretty common one that you'll see people use. It stands for tension, the tension in the cable. And now I'm going to go to the free body diagram for the 30 kilogram. We have a weight force down that's equal to 30 times 9.81, so that's 294.3. The ground is pushing on the wheels, so that's perpendicular to the surface toward the chosen body. I'll call that N30. Then that 300 Newton force that didn't act on the 15, it does act on the boundary of the 30. So we have the 300 here. And if I keep going around, the last place where there's contact is over here. That's a pulling force from the cable. So it's parallel to the cable, away from the body. And I'm going to give this a variable name, but here's, we had something like this with pushing, remember. I said that if two things are pushing on each other, then when you switch bodies, you use the same variable to represent that. Okay, that was related to Newton's third law. Cables, pulling forces, have something similar to that. When the same cable is attached to multiple bodies, you use the same variable for those. The magnitude of that force has to be the same. So I'm going to use this same T here. And that's going to be true whether the cable goes directly between them like this, or even if it passes through a series of pulleys, we're always going to make that assumption that those forces are the same. Okay, so let me get that in your notes. This is an important thing about cables. So notice, if the same cable let's say if the same cable is connected to two bodies, and in parentheses, let's say even if that cable passes over pulleys, the magnitude of the pulling force is the same for each body. Okay, so let me show you an example of how this works. So let's say we have two objects. One is a rolling cart on an incline. Let's say this has a mass of 10 kilograms. And then there's a pulley that connects this to a hanging mass. And let's say the mass is 5 kilograms. Draw a free body diagram of each of these two masses. Okay, so I'll start with the 10 kilogram. Here's the outline of the body. The weight force goes straight down. So the weight force is like this, and the magnitude is 10 times 9.81, so 98.1 newtons. There's a pushing force from the incline, and that means that the pushing force is perpendicular to the surface toward the chosen body. So here's a line perpendicular to the surface. Toward the chosen body means the vector is this way. And I'm going to give that the variable name n, fancy n. And then the last place the surroundings make contact with the boundary is the cable. That's a pulling force. So the rules of the direction say parallel to the cable, away from the chosen body, and I'll call that T. And now I'll do the free body diagram for the 5 kilogram. So here's the body. The weight force is 5 times 9.81 down. The pulling force is parallel to the cable, away from the body, so this way. And since it's the same cable as this one, we give it the same variable name T. Any questions about that? Let me show you one thing that's kind of interesting. I remember when I first took physics, I was sort of confused about the pulley thing because I remember I'd been told about pulley advantage that like pulleys, they're one of the like simple machines that, and they can have the effect of reducing the amount of force that you have to apply to something to lift it up. So I didn't really know what that meant, but I knew I'd heard that before. And now this way of treating cables going over pulleys just makes it clear that all a pulley does is change the direction of the force. So that confused me, like which of those is true? Well, all a pulley does is change the direction of a force, but there is a way to rig up pulleys so that the required force to lift something is less. So let me show you how that works. So this is pulley advantage. Okay, so first, let's think of ceiling with a pulley attached. And we're trying to support the weight of, let's make this thing 10 kilograms. And we just want to know what T has to be to hold this at rest. Okay. So free body diagram of the mass. We have the weight force down of 10 times 9.81. We have the cable force up, and it has to be the same as this T, so that's T. And now we'll put these into Newton's second law, and we have 0, negative 981, plus 0T is equal to the mass times the acceleration, and since we're just holding this at rest, the acceleration is 0. And so the y equation here says negative 981 plus t is equal to 0, so t is equal to 981. So there's no advantage there. This thing has a weight of 981 newtons, and that's the amount of force required to hold it up. Okay? But now I'm going to rig up 2 pulleys in a very specific configuration. Go away. So now this is the specific configuration that gives pulley advantage. So this time it's going to be the same mass. So here's the 10 kilogram mass. But this time it's going to be supported by a pulley there. And this cable is going to go under the pulley. And then there's going to be a second pulley here. And this cable is going to go over this one. And we're going to call this T. And now the question again is, now with this configuration, what's the T required to hold this mass at rest? Okay, well this time what I'm gonna isolate is like this. Everything I'm drawing the red line around. This is gonna be my free body. All this stuff that's hanging, okay, including the part of the cable that goes under the pulley. And so a free body diagram, I'm gonna draw the sort of piece of the cable coming out there. That's all included in what we're isolating. Okay. So the forces acting on this, first there's a weight force of 10 times 9.81, so this is 98.1. And now the cable is attached to the boundary at two different places, right? The cable that's not included is attached to the cable that is included here. So this force has to obey the rules for cable force. And since it's the same cable as this one labeled T, this has to be T. And then it's also attached here. The rules of a pulling force say that that's in that direction. It's the same cable, so that also has to be T. Now put this into Newton's second law, and you get 0T plus 0T, forgot the weight, plus 0, negative 981. This is 10. 10 times 9.81 is 98.1. Sorry about that. So put these decimal points in all these places. So this 98.1, that's what this should have been to 98.1, 98.1. And this is equal to the mass of 10 times the acceleration, and it's not moving. And so the y equation here says t plus t minus 98.1 is equal to 0. So 2t is equal to 98.1. And so t in this case is equal to 49.05. Okay, so it wasn't really exactly the pulley that made it so you could hold a heavy thing with less force. If you just set up a single pulley, you have to apply that same force just in a different direction to hold it up. But you can devise a system where you can reduce the force required to hold something up. Okay? All right, the last thing we have to talk about is friction. So this is a force that resists sliding along a surface. And there are two types of friction forces that resist sliding along a surface. The first one is static friction. Static means at rest. And so static friction is this is a friction force that prevents an object at rest from starting to slide. The second type is if the object is already sliding. This is called kinetic friction. And you can think of this as friction that tries to slow down an object that's already sliding. There's no particular reason that I'm going to choose one of these over the other. They're kind of both equally useful. One isn't any harder than the other. But in this class, we're just going to deal with kinetic friction. We're not going to deal with static friction. And that's just to save time. It's not it's kind of arbitrary. So when we talk about friction, we're always going to be dealing with a case where something is already sliding along the surface. And one thing that you'll notice, keep this in mind, friction always occurs along with a pushing force from the surface. Friction always occurs along with a pushing force from the surface. And that pushing force from the surface, I'm always going to give the name fancy N. Okay, and we're actually going to have to use that pushing force from the surface in our calculation of the friction force. Okay, so if you have kinetic friction, that's all we're going to do in this class. The direction of the friction force is always opposite the direction of the velocity. So it's always going to be parallel to the surface. This makes sense if you think about the fact that friction always is trying to slow things down. You never have the case where there's so much friction that something just suddenly accelerates to high speed. It's always trying to slow things down. So that force always has to act opposite the direction of motion. And the magnitude of the friction force is always this coefficient of friction, that's the Greek letter mu. Excuse me. Remembering Greek letters is always a pain, but remembering the letter mu is easy because you can't really tell whether I've drawn an M or a U, and that's how you spell mu. Okay, so that's the one you can always remember. So that's a Greek letter mu. And then you multiply that by that pushing contact, the normal force, the pushing from the surface. And so let me tell you what these are. This mu is called, this is always a positive number. It doesn't have any units. And it represents, you can think of it as kind of like the stickiness between the two materials in question. The two materials in contact. And this mu is called the coefficient of kinetic friction. It's usually between 0 and 1, but in some cases it can get a little bit bigger than 1. But usually it's going to be, you know, a decimal, a fraction. And then N is the normal force pushing the materials together. Okay, so before I do a free body diagram with these, we have everything we need for a free body diagram, but I do want to just kind of point out why the magnitude of this friction force kind of makes sense. So let's think about this stapler sliding along the table. We'll do this one. Okay, so what this magnitude says is for the same two materials in contact, the friction force gets bigger as the two things are pushing harder against each other, as that pushing force between them gets bigger. So right now, the pushing force from the table onto this just depends on the weight of the stapler, which isn't very big, okay? So if I slide this along, there is some friction, but it's pretty easy for me to slide this along the table, okay? But now imagine trying to slide it along the table if I push down on this with all of my weight, okay? I'm not applying a horizontal force to it, I'm just pushing straight down. So I'm not directly making it harder for this to slide. But if I push down on this, the normal force, the pushing force between the table and the stapler gets bigger, okay? And as that force gets bigger, your intuition tells you that it becomes harder to slide this, okay? And so that's kind of the connection between your intuition and the math there. What this formula is saying is, if those two things are pushed harder together, the friction force gets bigger, okay? All right, this is the last thing we'll do, and then I'll go get the quizzes. So, let's say we have a block that's sliding along this incline. And let's say that the direction of motion of this block at this instant is up the ramp. In other words, that's the direction of the velocity. And let's say that this has a mass of 10 kilograms. And let's say that the coefficient of friction for this incline and this block is 0.3. And we want to draw a free body diagram. Okay, well, the first thing is you might think, like you think about the forces going on. The weight force would try to slide this down the ramp, you know? So how could this thing be going up the ramp if weight is trying to send it down? Well, the reason that's possible is the velocity, remember, doesn't depend on the forces. Velocity depends on forces that existed in the past. The only thing that depends on the forces is the acceleration. So something like this could happen because a force had been applied for a while to get it sliding fast up the hill, and then that force was removed, but it still has, it's still sliding. It hasn't stopped all the way yet. Okay, so just remember that with forces and stuff, you can't calculate anything about velocity. That has to be provided for you. You can only calculate stuff about acceleration. Okay. If you knew the forces over a period of time, you could calculate the acceleration and do some calculus stuff and calculate the velocities, but we're not doing that kind of stuff. Okay, so free body diagram. There's a weight force down of 98.1. And then go around the boundary looking for contact. The only contact is with the surface. And so there's going to be, in this case, a friction force and a pushing force. The pushing force is perpendicular to the surface toward the chosen body. And I'll give that the name fancy N. And then the friction force is opposite the direction of motion. So that's this way. And the magnitude is the coefficient times that normal force. Okay. And be sure you are noticing that this isn't saying 0.3 newtons. That's saying 0.3 times that pushing force. Like, people always make that mistake on this test that's coming up, so don't be one of the people that makes that mistake, okay? That's not newtons, that's the pushing force.
Wait, so fancy N is redwood force or?
Fancy N always represents a pushing force from a surface. Plain N is newtons.
Okay.
Yep. Any other questions about this? Okay, that's it.